So, today one more application of operational amplifier and integrator. Integrator is the one of the example for linear applications of op amp. Right? The name itself explain what is integrator. Right? Integrator is a circuit whose output voltage is the integration of input signal. Integrator is the output whose output voltage is the integration of the input signal. So the integrated circuit can be obtained without any active device like op amp and transistors. Such a case that integrator is called passive integrator. If you use active devices like op amp, this this integrator is called active integrator. Active integrator, right? If you are not using any operational amplifier or a transistor, it is called passive integrator. Suppose take this resistor, a capacitor, right? So you are applying VA. You are measuring output. So what is this circuit? Anyone? What is that circuit? Anyone? What is that circuit? Hmm. You are right. Repeat it again.
Low pass filter.
Low pass filter, right? It is low pass filter. So it is also acts as an integrated circuit. This low pass filter is also acts as an integrated circuit, right? So this is called passive integrated circuit. This is called passive integrated circuit. The same thing will be replaced with the help of operational amplifier. With the help of operational amplifier. If you observe, this is the ideal integrator, ideal active integrator, ideal active integrator. Suppose active integrator. If you observe the components R and C, similar to your passive integrator. But the thing is, the difference is op amp, which is active device, which is active device. That's why this entire circuit is called circuit diagram of active integrator. Circuit diagram of active integrator. Okay, right? Is it clear? So what is the output? What is the expected output of this active integrator? Integration of V dt. That means output is integration of input signal. Is it clear, all of you? What is integrator? Is it clear, all of you? Is it clear? Respond.
Yes, sir.
Right. Now, coming to analysis. Coming to the analysis. So this one is basic integrated circuit. We are having two integrated circuits. One is ideal integrator and second one is practical integrator. So the drawbacks, the limitations of ideal integrator are overcome by the practical integrated circuit. So by doing some modification of this circuit, we'll design the practical integrator. First, initially, we'll look into the ideal integrator circuit, right? So this is the ideal integrator circuit. If you observe, the non-inverting input terminal is grounded. Non-inverting input terminal is grounded. Nothing but VB equal to 0. VB equal to, right? Then tell me, what is the voltage at this point? What is the voltage at that point? This one,
0.
right? It is 0. It is 0, right? This is what I have written here. VA equal to VB equal to 0. Next, so I think is it clear? It is clear. Now, here the current through R1 I'm considered as I. Here the current through R1 is considered as I. What is the current through op amp? What is the current through op amp?
0, sir.
0. Then what is the current flowing through your capacitor? Which is same as this current, isn't it? Isn't it? Which is same as current through R1. Are these currents are equal or not? Equal or not?
Equal, sir.
Right. Now write the equations similar to previous one. What is I? V in minus VA by R, where VA is 0. Where VA is 0. Right. Now the current through op amp is 0. Now the current is flowing like this. The current is flowing. What is the current equation for current flowing through the capacitor? What is the equation for the capacitor? The current
C
flowing
into
through the,
dV by dt.
right. I equal
C
to,
dV by
right, C dV by dt. C dV by dt. So I equal to C, nothing but here feedback capacitor, CF d by dt. Change in voltage. Change in voltage ఎక్కడి నుంచి ఎక్కడికి వెళ్తుంది current? From VA to V0. From VA to V0. So d by dt of VA minus V0. So what is VA? 0. So what we get? Minus V0. So minus CF into dV0 by dt. Is it clear up to this point? Second equation. Is it clear?
yes, sir.
Then these two currents are equal. We know that. Kada? The two currents equal. Then we equate equation 1 and 2. Right? Take the integration on both sides. Take the integration on both sides. So this derivative and integration get cancelled. So integration of V in by R1 dt minus CF into derivative and integration get cancelled. We are having V0 term only. Right? We have to calculate output of the integrator, right? So V0 equal to, you take minus CF to left hand side, we get V0 equal to minus R1 CF integration of Vn of t, right? So where R1 CF is time constant of the system. R1 CF is time constant of the system. This constant. Okay, tau equal to RC kada? Idea on the time constant.
Yes, sir.
Right. This one is time constant of the system. Then tell me, why we are getting negative sign here? Why you are getting negative sign here?
Inverting amplifier.
No. Yes, your input is applied to inverting input terminal. Inverting input terminal. So that's why you are getting 180 degree phase shift represented with negative sign. So the output of an integrator, the output of integrator is minus 1 by R1 CF times of integral of input. If you observe this one, output is minus R1 by R1 CF times the integral of input. R1 CF is called time constant on the integrator. Negative sign indicates 180 degrees shift between input and output. Is it clear, all of you? How you get output in terms of integration of input for an integrator? అర్థమైందా ఇప్పుడు ఇంటిగ్రేటర్ అంటే ఏంటో?
Yes, sir.
Right, output is integral of input signal. The difference ఏంటి? Simple difference inverting amplifier కి దీనికి, in the place of RF you are replacing CF. In the place of RF you are replacing CF. That's the only small difference between inverting amplifier and ideal integrator. Is it clear, all of you, the difference? Right, let us apply various types of input signals. Vin various apply chain. First Vin different waveforms ki output waveforms ఎలా వస్తాయో we will observe. Step input step signal apply చేస్తే output ఏం వస్తుంది? Integrator output. Next square wave apply చేస్తే, if we apply square, what is the output waveform? If you apply sine as Vin, what is V0 of an integrator? Okay, so V0 ఎలా వస్తాయి ఈ 3 inputs కి? Let's see. So very important for competition exams, right? So first I'm applying step signal. For simplification of analysis, I'm taking this R1 CF as 1. Okay, for simplification of analysis I'm assuming time constant equal to 1. Is it clear? So what is the output finally? If R1 CF equal to 1, V0 equal to minus of VA, minus nothing but 180 degrees phase shift, minus V in dt. Is it clear? So now we'll apply various input signals. So first let us see step input. Step input. So what is step input? You know, you are well aware of this type of signal. Step input whose magnitude is constant when t is greater than or equal to 0. When t is greater than or equal to 0, the magnitude of step signal is constant, and 0 when t less than 0. So if you observe t less than 0 side, your input signal is 0, your input is 0. But at t equal to 0, your input is a, and t greater than 0, your input is a. Right, now apply this step input signal to your integrator. This is the integrator formula. Integrator V0 equal to minus of, in the integral intervals I'm taking from 0 to t V in into dt. So V0 equal to, what is the magnitude of input signal? A, which is constant. Step kada, so it is constant. The magnitude is a. Okay, so I'm taking input a. If you integrate a constant term, we are getting a is taken out from the integrator, then which becomes t minus 80. V0 equal to minus 80. Is it clear? Right, your V in is a at t greater than or equal to 0. T greater than or equal to 0. What is V0? Minus a t, minus a into t. Negative sign means it is 180, and in చెప్పాం కదా inverting integrator kanuka, right? So if you plot the graph like this, if you plot the graph, it is t, it is V0, it is 1 time period, time t equal to 1, t equal to 2, t equal to 3, it is intervals, t equal to 4, right? So If it is minus a magnitude, output magnitude minus 2a minus 3a. Right. So t equal to 1, at t equal to 1, what is V naught? What is V naught? At t equal to 1, what is V naught?
Minus A, sir.
So minus a, I'm pointing here. At t equal to 2, what is V naught? At t equal to 2,
minus 2a, sir.
minus 2a. At t equal to 3, at t equal to 3,
minus 3a, sir.
minus 3. At t equal to 4, t equal
Minus
to,
4a, sir.
at t equal to infinite, at t equal to infinite,
Minus infinity, sir.
minus infinity. ikkada minus infinite undi. So if you join these points, so what is this one? Negative slope, and this one is a ramp signal. This one is a negative ramp. So if you apply step input to your integrator, what is the output? If you apply input to your step input to your integrator, what is the type of output signal you are getting? Tell me.
Straight line.
Straight line. దాన్ని ఏమన్నాను ఇప్పుడే?
Negative ramp signals.
Ramp signal. So integral, I mean inverting type kanaka, we are getting negative ramp. We are getting negative ramp. Is it clear for step input? Is it clear, all of you?
Yes, sir.
Then apply square wave. Apply square wave. This is the square wave. Yeah, this one is plus a magnitude, and this one is minus a magnitude. So I'm dividing the waveform this into this intervals. So tell me, 0 to t by 2, what is the input magnitude? 0 to t by 2, what is the input magnitude? Input signal magnitude 0 to t by 2.
Yes, sir.
Right. That's what I have written here. 0 to t by 2. Then t by 2 to t.
Minus a.
Minus c. Then tell me, if you apply input is a from 0 to t by 2, what is the output? 0 to t by 2, what is the output?
Negative ramp.
Negative ramp. So that's why I'm getting negative ramp. Similar to this one. మనకు జనరల్గా ఇదేమో ఇందాక స్టెప్ సిగ్నల్ మనకి ఇలా ఉంది, లైక్ దిస్, అప్ టు ఇన్ఫైనైట్ ఏ కాన్స్టెంట్ మ్యాగ్నిట్యూడ్, అప్ టు t ఈక్వల్ టు 0 టు ఇన్ఫైనైట్ విత్ కాన్స్టెంట్ మ్యాగ్నిట్యూడ్. బట్ స్టెప్ అనేది స్క్వేర్ అనేది 0 టు t by 2 పాజిటివ్ ఉంది, ఫ్రమ్ t by 2 టు t నెగిటివ్ ఉంది, రైట్? దెన్ టెల్ మీ t by 2 టు t, వాట్ ఈస్ ద అవుట్పుట్? t by 2 to t input and a negative magnitude minus a, what is the output?
Positive ramp.
Right. Why you are getting positive? Already we are having minus outside, so minus of minus a dt. Vin అంటే ఏంటి ఇక్కడ? మైనస్ ఏ. ఎక్కడి నుంచి ఎక్కడి వరకు? t by 2 to t, t by 2 to t. Okay, right? t by 2 to t. What is the minus of minus a dt? So minus minus plus. So what is the expected output? V naught from t by 2 to t? 80. 80. Is it negative ramp or positive ramp? Negative ramp or positive ramp? 80.
Positive ramp.
So that's why you're getting positive ramp here. Then t by 2 to 3t by 2. Negative ramp. Then 3t by 2 to 2t. Right. If you observe this one, we are applying input is square wave. What is the output of integrator if you apply square wave? అది ఎలా ఉంది? సపోజ్ ఇది మళ్ళీ ఇక్కడ డౌన్ అయింది, మళ్ళీ ఇలా పెరిగింది, మళ్ళీ ఇలా అయింది. Leave it this part, then how? Right, your output is triangular wave. What is the input? Square wave. What is the output of integrator if you apply square wave as input?
Triangular.
If you apply step signal as input, what is the output?
Negative ramp.
నెగిటివ్ అని వదిలేను, అది అనేది ఇన్వర్టింగ్ కనుక నీకు నెగిటివ్ అంటున్నాను. అదే
So
నాన్
ramp.
ఇన్వర్టింగ్ అయితే ర్యాంప్.
Ramp.
ఇది క్లియర్? మౌలి, ఓకే, రైట్. సో is it clear, all of you?
Yes, sir.
Now apply sine wave, amma. Now it's time to sine wave. Sine wave, I am applying sine wave as the input to your integrator, right? And I am dividing this to one like this: 0 to t by 2 positive cycle, t by 2 to t negative cycle, t to 3t by 2 positive cycle, 3 to 2 by 2 to 2t negative cycle. Okay, and the magnitude of the sine signal is plus Vm and minus Vm, plus Vm and minus Vm. Okay, so let us take your pure sinusoidal signal, which is Vn equal to Vm sin omega t, Vm sin omega t, right? Then derivative, I mean find the integration, minus of b in dt, right? So that means minus of Vm sin omega t dt. Okay, Vm is constant, take to outside, so minus Vm integral of sin theta, integration of sin theta ఏంటమ్మా? Integration of sin theta
Minus cos.
minus cos theta, right? So tell me, integral of sin 80, what is the output here? Integration of sin 80,
Minus cos 80 by 8, sir.
right? Minus cos 80 by a. Similarly, minus cos omega t by omega. Is it clear? Minus cos omega t by omega, right? So this minus becomes plus Vm by omega into cos omega t is your output, is your output. So input is sine. What is the output you are getting? Output of integrator. What is the output of integrator? If the input is sinusoidal signal, sine signal, what is the output of integrator?
Cos signals.
Cosine signal, cosine wave. Okay, output is cosine wave. Input is sine wave to your integrator, output is cosine wave, right? Tell me, now we'll plot this one like this. If you observe, it is 0 point, it is the 0 position, right? What is the output here? If place 0 here, t equal to 0, what is the output here? What is the output? What is the output here? T equal to 0. What is the output?
Vn by omega, sir.
Right. Cos 0 how much?
1, sir.
1. Vm by omega. So that's why at 0 I am taking this one is Vm by omega. Okay. So this one is minus Vm by omega. This one is plus Vm by omega. Okay. So Vm by omega. Now at this point, what is the value here? If you take the angles in terms of angles, ఇక్కడ ఎంత యాంగిల్ ఉంటుందమ్మా?
Pi by 2, sir.
Pi by 2. Cos pi by 2 ఎంత? Cos pi by 2 how much?
0.
So that's why it drops to 0 here. It drops to 0 here. Then tell me, what is the angle here at this point?
Pi.
Cos pi how much?
-1, sir.
-1. Cos 90 plus theta minus sin theta. That means sin 90, right? Cos 90 plus 90 minus sin 90, which is -1. We get minus Vm by omega. So that's why at 180 degrees we are getting -1. Then అలా మనం ప్లాట్ చేసుకుంటూ వెళ్తే we are getting cosine. We are getting cosine signal. So what is the output of integrator if the input is step signal?
Ramp signals.
Ramp. What is the output of integrator if the input is sine wave?
Triangular, sir.
Cosine, sir.
ఏం
Cosine,
బట్టి
sir.
పట్టారు మాట
Cosine wave, sir.
cosine wave. Question వినండి తల్లి. What is the input? What is the output of integrator if the input is step signal?
Sir, ramp, sir.
What is the output of integrator if the input is square wave?
Triangular, sir.
Triangular, sir.
Right. Good. So that's what I mentioned here. So can a table చూసారు కదా? Vn step అయితే output ramp, square wave అయితే triangle. వెరీ ఇంపార్టెంట్ ఆబ్జెక్టివ్ క్వశ్చన్స్ అమ్మ, గుర్తుపెట్టుకోండి, మీకు ఆన్లైన్స్ లో కూడా అడుగుతారు. ఓకేనా? డోంట్ గెట్ కన్ఫ్యూజ్. మళ్ళీ డిఫరెన్షియేటర్ డిఫరెంట్ గా వస్తాయి మనకి. ఓకే, డిఫరెన్షియేటర్ కి డిఫరెంట్ గా వస్తాయి. ఇంటిగ్రేటర్ కి ఇలా డిఫరెన్షియేటర్స్ కూడా ఇన్పుట్స్ ఇవే కానీ అవుట్పుట్స్ మారుతాయి. ఓకే, ఇజ్ ఇట్ క్లియర్? Is it clear?
Yes, sir.
Right. Now we'll plot frequency response for this integrator circuit. We'll plot the frequency response of this ideal integrator circuits. Right? మనకి లిమిటేషన్స్ ఏం వస్తాయి, ఆ లిమిటేషన్స్ ఓవర్కమ్ చేయడానికి మనం కొన్ని మోడిఫికేషన్ చేయాలి ఈ ఇంటిగ్రేటర్ సర్క్యూట్. దట్ ఈస్ కాల్డ్ ప్రాక్టికల్ ఇంటిగ్రేటర్ సర్క్యూట్. ఓకే, ఫస్ట్ మన ఆ లిమిటేషన్స్ ఏంటి దానికోసం let us draw the frequency response. Right. What is the output of integrator? This one is output of integrator. V naught equal to -1 by R1 CF integral of V in into dt. Okay. So now I am taking same output in terms of time domain. In terms of time domain. Time domain అంటే ఏం లేదు, V naught of t వస్తుంది, Vn of t వస్తుంది. ఓకే, సో అంతే కదా. ఫ్రీక్వెన్సీ డొమైన్ ఫ్రీక్వెన్సీ రెస్పాన్స్ ఏ డొమైన్లో క్యాలిక్యులేట్ చేస్తాం? ఏ డొమైన్లో క్యాలిక్యులేట్ చేస్తాం ఫ్రీక్వెన్సీ రెస్పాన్స్? కంట్రోల్ సిస్టమ్స్ డ్రా చేశాం కదా ప్లాట్స్, ఫ్రీక్వెన్సీ రెస్పాన్స్. అక్కడ దాకా ఎందుకు? కరెక్ట్ చెప్పండి. ఎస్ డొమైన్. సో టైం డొమైన్ నుంచి ఎస్ డొమైన్ చేయాలంటే ఏం అప్లై చేయాలి?
Laplace transform.
Laplace transform apply చేయాలి, right? So that the same thing here I'm doing. So first I'm writing the your output of integrator in time domain, v naught of t, v in of t, and taking Laplace transform, which is v naught of s minus integral కి Laplace ఏమొస్తుంది 1/s వస్తుంది, అంతే కదా, అంతేనా అంతేనా. Laplace of integral of a dt. What is the Laplace of integral of a dt? a by s, అంతేనా. అదే డిఫరెన్షియేషన్ అయితే డిఫరెన్షియేటర్ అయితే ఏమొస్తుంది as. ఇదే కదా మీరు మ్యాథమెటికల్ మోడలింగ్, ఫోర్స్, కరెంటు, వాటి ట్రాన్స్లేషనల్ రొటేషనల్ సిస్టమ్స్లో చేసాం కదా, సేమ్. డిఫరెన్షియేటర్కి అయితే a ఇంటూ s వస్తుంది లాప్లాస్ ట్రాన్స్ఫార్మ్, ఇంటిగ్రేషన్కి అయితే a బై s వస్తుంది, అంతేనా. a dA బై a లాప్లాస్ ట్రాన్స్ఫార్మ్ wait a minute, wait a minute. Okay, so right, so I'm applying Laplace transform to this equation. Time domain change it to s domain, and this integral becomes 1 by s into r1 cf, v of t becomes v of s. Okay, then frequency response calculate cheyadaniki we know that s is replaced by j omega, s is replaced by j omega. So v naught of j omega by minus 1 by j omega r1 cf v in by j omega. To take v in to your left hand side, we are getting like this, minus j omega means 2 pi f, right? To calculate magnitude of this, so this one is square root of 0 square plus 2 pi f r1 cf whole square. So 0 square, so this square, this root cancel, finally you are getting 1 by 2 pi almost. So which is the gain? Which is the gain? Okay, which is the gain? Is it clear up to this point? A equal to 1 by 2 pi f r1 cf. Is it clear? Is it clear?
Yes, sir.
Right. Done. So see, వాడు ఏం చెప్తున్నాడు, at low frequencies such as DC signal f equal to 0, what is the gain f equal to 0 for DC signal? 1 by 0. 1 by 0 means 1 by 0 means 1 by 0. What is the value?
Infinite.
Infinity.
Infinite. So when for DC signal, your gain becomes infinite. Okay, so this is because capacitive reactance becomes very high for low frequencies. Capacitive reactance very low for high frequencies. Ante kada? Sorry, very high for low frequencies. What is capacitive reactance? 1 by omega c. Antena? 1 by 2 pi f into c. Low frequencies, this is the capacitive reactance frequency. Are they inversely proportional or directly proportional? Are they inversely proportional or directly proportional? Frequency and reactance. Frequency and reactance, are they directly proportional or inversely proportional?
Inversely proportional.
Right. If F equal to 0 for DC, what is reactance?
Infinite.
Right. Infinite. If this is not 0, suppose some frequency 1 Hz, very low value. What about reactance?
I, sir.
Right? So is it clear? So suppose this is the reactance of this capacitor. Reactance of this capacitor. Reactance nothing but the resistance, like that. Ante kada, reactance is nothing but the resistance. If it is infinite, if it is large, what about the current flowing through this reactance, high reactance path? Current also inversely proportional to 1 by R, resistance or reactance, right? So this one is infinite. What about current? What about current? If it is infinite, what about current?
0, sir.
Current is 0. If it is large, what about current? If it is large, resistance is large, resistance or reactance are large, is large. What about current flowing through this component?
Small.
So that's why it acts as, it operated in, your operational amplifier operated in so what is the type of configuration, this one? It is open because of infinite resistance or high reactance or infinite reactance. It is open. So what is the type of configuration here? What is the type of this configuration? Item configuration, item configuration. Basic, I'm asking. What is the type of configuration? Iday configuration lo undi, iday configuration lo undi. Brains ku pani cheppandi. Basic, I'm asking.
Open loop, closed loop.
Right, good, very good. This is open loop configuration, this is closed loop configuration, but it is happened when frequency is 0 or frequency is low. Frequency is low, your this circuit becomes the feedback. Whenever it becomes open, this diagram becomes like this. This is that means op amp operated in open loop configuration for low frequencies. That's what I want to say, right? So here what is I am explaining is the same thing. See, at low frequencies the gain becomes infinite. Ante kada open loop configuration gain ఎంత ఉంటుంది మీకు ఎప్పుడు, అందుకే అవుట్పుట్ ఆల్వేస్ ఇన్ సాచురేషన్, బిట్వీన్ సాచురేషన్స్ వాల్యూస్ దగ్గర మీకు అవుట్పుట్ వేరీ అవుతూ ఉంటుంది, ప్లస్ విసాట్ మైనస్ విసాట్, బికాస్ ఆఫ్ లార్జ్ గెయిన్. అదే చెప్తున్నాడు, డిసి ఈక్వల్ టు 0 ఫర్ దిస్ ఇంటిగ్రేటర్, gain becomes infinite. This is because of capacitor reactance, it becomes very high for low frequencies. Hence it acts as an open circuit and op amp works in open loop configuration, and the open loop gain of op amp is almost infinite. Is it clear, all of you? These 4 lines. Is it clear?
Yes, sir.
Right. See, as the frequency increases, the gain drops and response is similar to that of low pass filter, right? Frequency increase అవుతుంటే మనకు frequency response ఎప్పుడు ఎలా ఉంటుంది? డ్రాప్ అవుతూ ఉంటుంది, gain is dropping, right? So let f equal to fb be the frequency at which gain of the op amp becomes 1, that is 0 dB. So I'm taking at this frequency f equal to fb, అదంతానే నాకు తెలియదు వాల్యూ, ఓకేనా, న్యూమరికల్ వాల్యూ. లెట్ ఎఫ్ ఈక్వల్ టు ఎఫ్బి at that particular frequency the gain drops to 0 dB, that is 1. 0 dB means normal value is 1. Okay, so see at f equal to fb 20 log this one, 20 log this value at f equal to fb kada. So f equal to fb, f equal to fb, which is 0 dB. I'm taking at f equal to fb, at f equal to fb the gain becomes 0 dB. Okay, let f equal to fb, that at particular frequency the gain of op amp becomes 0 dB. That's why I'm equating this, I'm writing like this 20 log dB అంటే 20 log కదా, 20 log a కదా. సో a అంటే ఎంత వచ్చింది మనకి ఇందాక ఇక్కడ అనాలిసిస్ లో, how much we get, a is 1 by 2 pi r 2 pi f r1 cf. So at f equal to fb, and that means 1 by 2 pi fb r1 cf. So 20 log 1 by 2 pi fb r1 r1 sorry, this one is f. Wait a minute. Mistakes. This one is f. This one is also f. This one is also f. Cf. Okay. So at f equal to fb, gain is 0 dB. So 20 log 20 it's తీసుకెళ్తే ఏమవుతుంది, 0 అవుతుంది. log base to 10, log అటు వెళ్తే ఏమవుతుంది, 10 power 0, which is 1. 0 dB అంటే ఏంటి, 1 కదా, right? So 1 by 2 pi fb r1 cf equal to 1. From this, what is fb? fb is nothing but 1 by 2 pi r1 cf. So at this frequency your gain reaches to 0 dB. This is the fb. Usually it is 1 megahertz for 7 op amp. Usually it is 1 megahertz. ఇదే కదా యూనిటీ గెయిన్ బ్యాండ్ విత్ అంటాం, మనం నేర్చుకున్నాం స్టార్టింగ్ లో, 1 megahertz, right? So the gain drops from high value to low value with the slope of minus 20 dB per decade, minus 20 dB per decade. If you draw the 3 dB line, so you are getting 3 dB bandwidth is very, very small. 3 dB bandwidth is very, very small, right? This is the limitation. The 3 dB bandwidth is very small for an ideal integrator. This is one of the limitation of ideal integrator. Okay. So the ideal integrator frequency response like this, like slope, right? This is the maximum value. If you draw the 3 dB, this one is bandwidth, so this is very small for an ideal integrator. And the 0 dB frequency is fb. అది మనం అనుకున్నాం, let f equal to fb, the frequency at which gain of the op amp becomes 0 dB. Okay, so it can be seen from the response, the 3 dB bandwidth of an ideal integrator is very small. This is one of the limitation of ideal integrator, right? So what are the limitations? Another limitations, right? We know that these are the factors which affect the output, these are the factors which affects the output of your op amp. So because of these factors, we are not getting perfect integration of not input signal. We are not getting true integration of input signal because of these factors: input offset voltage, input offset current, input bias current, which are available at this point. I mean which are available at these positions, right? ఇన్పుట్ బయాస్ కరెంట్ కానీ ఇన్పుట్ ఆఫ్సెట్ కరెంట్ కానీ మనకి ఎప్పుడు ఇన్పుట్స్ దగ్గరే ఉంటాయి, అవునా? సో ఆ కరెంట్స్ వల్ల మనకి ప్యూర్ ఇంటిగ్రేషన్ అనేది పాసిబుల్ అవ్వదు. ప్యూర్ ఇంటిగ్రేషన్ అనేది పాసిబుల్ అవ్వదు అంటే మీరు స్క్వేర్ ఇస్తే ప్యూర్ ట్రయాంగులర్ వేవ్ అనేది రాకపోవచ్చు, సైన్ ఇస్తే ప్యూర్ కొసైన్ అనేది రాకపోవచ్చు, మేబీ సమ్ లిమిటేషన్స్ ఉంటాయి. సో టు ఓవర్కమ్ ద డ్రాబ్యాక్స్, దీస్ టూ డ్రాబ్యాక్స్, దట్ మీన్స్ to avoid the effect of these three parameters on integrator, ఇదంతా చదివినా అదే నేను చెప్పేదే ఉంటుంది, నో నీడ్ ఆఫ్ ఇట్. సో ఇది ఇన్పుట్ ఆఫ్సెట్ వోల్టేజ్ కానీ ఇన్పుట్ ఆఫ్సెట్ కరెంట్ కానీ ఇన్పుట్ బయాస్ కరెంట్ కానీ దే మే ఎఫెక్ట్ ద output waveform. That's why what is the here the same thing here explaining, output waveform may be distorted due to such an error voltage, అంతే కదా. వీటి వల్ల ఏమవుతుందంటే యాంప్లిఫైర్ కదా, ఇది ఆపరేషన్ యాంప్లిఫైర్ విత్ హై గెయిన్ కదా. సో దోస్ ఎర్రర్ ఐ మీన్ ఈ వెరీ నెగ్లిజిబుల్ వాల్యూస్ కదా, మిస్ మ్యాచింగ్ ఆఫ్ కాంపోనెంట్స్ వల్ల రావచ్చు, ఎఫెక్ట్ ఆఫ్ టెంపరేచర్ వల్ల రావచ్చు, ఎఫెక్ట్ ఆఫ్ వేరియేషన్ ఇన్ దట్ సప్లై వోల్టేజ్ రావచ్చు, రైట్? సో రైట్, సో పర్ఫెక్ట్ ట్రాన్సిస్టర్స్ క్యారెక్టర్స్ మ్యాచ్డ్ ట్రాన్సిస్టర్స్ యూజ్ చేయకపోయినా రావచ్చు ఇంటర్నల్ స్టేజెస్ లో ఆప్ యాంప్. సో those are some considered as very negligible currents or negligible voltage which are also called some errors. సో అవి కూడా యాంప్లిఫై అయ్యి అవుట్పుట్ కి ఎడిషన్ అవుతాయి ఇవి యాంప్లిఫై. దట్ మీన్స్ ప్యూర్ ఇంటిగ్రేషన్ ఈస్ మే నాట్ పాసిబుల్. అనదర్ లిమిటేషన్, bandwidth is very small, 3 dB bandwidth. Hence, an ideal integrator can be used for very small frequency range of inputs only. Because of this small bandwidth, ideal integrator is applicable, is useful for low frequency range of applications. Low frequencies range of applications. To overcome this limitation, we can use some additional components along with your basic integrator. సో ఈ బేసిక్ ఇంటిగ్రేటర్ సర్క్యూట్కి మనం కొన్ని మోడిఫికేషన్స్ చేసి ఆ లిమిటేషన్స్ని ఓవర్కమ్ చేయడానికి మనం మోడిఫై చేస్తాం. దట్ మోడిఫైడ్ ఇంటిగ్రేటర్ సర్క్యూట్ ఈస్ కాల్డ్ ప్రాక్టికల్ ఇంటిగ్రేటర్ సర్క్యూట్, which will be discussed in the tomorrow class along with the frequency response of practical integrator and with a problem. Okay, is it clear today's class? Is it clear all of you? Is it clear? So that's it for today. We'll meet you tomorrow. Okay, bye, take care.